So we're going to talk about the CAST project, CAST standing for carbon-14 source terms. So motivations, many safety assessments carried out by waste management organisations indicate carbon-14 is a radionuclide of some concern. So this was a good motivator for undertaking a bespoke project that looked at studying how carbon-14 could be produced from a range of materials commonly found in inventories. So we had some basis to work on, but we really wanted to look at carbon-14 from a number of different source terms and see if we can enhance the robustness of our understanding of how this radionuclide could behave in repository conditions. So CAST aimed to improve the understanding of the potential release mechanisms of carbon-14 from radioactive waste materials. And the project focused on release of carbon-14, both dissolved and gaseous species from irradiated metals, that's being steels and zircaloys, from ion exchange materials, and from irradiated graphite. WP stands for work package, so we broke down the problem into a number of different work packages, and the results were evaluated in the context of national safety assessments in work package 6, and an important aspect of the program was dissemination of the results, which was undertaken in work package 7. So this is my acknowledgement page, which I've put at the start rather than the end, but CAST had a number of participants. So 33 organisations with a range of skills and competencies in the management of radioactive wastes containing carbon-14 and geological disposal research. So we had national waste management organisations, research institutes, universities and commercial organisations. Let's see if this is going to work. So you might not see this, but we're looking really here at carbon-14 coming from the source term, graphite, steels. Didn't look at other source terms, so we were looking mainly at the metals. We haven't shown spent ion exchange resins, but we're trying to understand the story of how carbon-14 could be produced from the source term in a repository environment, and that then will be taken up and used in assessments of near-field performance, biosphere and geosphere behaviour. So we're really looking at part of the carbon-14 story here within CAST, but not forgetting that there are other aspects to the story that we also need to consider. So CAST experimental work packages looked at the inventory of carbon-14, how much, in what form, how is it distributed, how it was released, what's the mechanism of release, what's the speciation of what the material that's released, and sort of possible transportation and subsequent reactions. So now I'm going to do a very whistle-stop tour through each of the technical work packages, that's 2, 3, 4, 5, and then a couple of slides on safety assessments and also on the dissemination. So work package 2 was led by NAGRA and considered irradiated steels. So various aims to start with. We wanted to do a state-of-the-art review. We wanted to advance our understanding of carbon-14 speciation, develop analytical techniques, measure release rates, and confirm measure inventories. As with anything that, well, many things you start, they seem conceptually quite simple, and you undertake them and you realise it's actually quite difficult. So there are a number of challenges that the project had to overcome, not least obtaining and working with samples. We also have to measure release rates when the release rate itself was actually very, very low, and consider various other aspects of carbon-14 behaviour. I'm not going to read them all through, but there are many challenges. A number of teams participated in each work package, which is beneficial. So these are some of the teams participating in work package 2, and a range of different conditions for the release mechanisms that were being investigated for the irradiated steel samples. And also stainless steel and carbon steel. We had a range of materials. And this just looks at some of the results. So we're looking at the release of carbon-14 and also carbon-12. What species you're getting off, the percentage of liquid phase versus gas phase species. So, at the end of the project, what do we actually learn from steels? Well, some of the highlights, we did actually obtain some samples and made some carbon-14 measurements, on activated samples. We improved our understanding of the release of carbon-14, undertook a microstructural characterization of the irradiated material and where the carbon-14 is located, had an improved understanding of the inventory, and another good understanding of the rate of corrosion under disposal conditions. And all these studies are reported on work that's freely available, at the moment still freely available. And for each work package, we produced a synthesis report. So if you did want a one-stop shop, looking at the results that we obtained for any one of these particular materials, there's a link there, and there's a link towards the end of the project, towards the end of the presentation, that gives you the website you need to look at. Zircaloys, the work package 3, this is work led by Ondra. Some similar issues that we had to those found with steels. Challenges were obtaining and working with the samples, looking at release rates that were extremely slow. So a number of challenges we had to work our way through as part of the project. Again, a range of organizations, which is good, it allows you into comparison of results. Range of different solutions. And these were the sort of species that we were finding. Organics and inorganics, some in the gas phase. A number of analytical techniques were undertaken. So again, working together over a sort of 3 or 4 year project, we managed to enhance the database and knowledge base on the materials we're looking at, in this case zircaloys. And we've also managed to provide some more information on leach rates. So we can do some longish term experiments. I'm sure you'd like to do some longer term experiments, but there are some longish term experiments that were undertaken to give some better indication of corrosion rates of zircaloys that can be considered subsequently in sort of performance assessment safety case work. So some of the highlights. Getting hold of the samples shouldn't be underestimated. I lost my pointer. There you go. Some good agreement between measured and calculated inventories, good database of long-term corrosion rates, some information that suggests the instantaneous release fraction, that is typically used in some of the performance assessment calculations is high, and that perhaps we ought to readjust it to 7.5%. And again, a synthesis report if you just want a one-stop shop for all the work we've done. Work package 4 looked at spent ion exchange resins. Again, we started with a state-of-the-art review. I think in this case there was a challenge because there was a wide range of characteristics due to different types of operating plants and different IX locations within any one given plant. And I think this did manifest itself in the results we got and the transferability of some of the results we got. You really need to look at the carbon-14 presence in spent ion exchange resins on a sort of country-specific inventory basis and on a speciation basis. It's an issue that's very much affected by the circumstances of that it's experienced within a reactor. There's a good understanding of speciation in general, and in general the majority of carbon-14 present is inorganic, but the fractions depends on reactor type, so you can get quite a big variation depending on the reactor type, and also depending on the history of the spent ion exchange resin investigated. And again, there's a synthesis report for a sort of one-stop shop. The sort of final technical work area we looked at was irradiated graphite. This built on the EC carbo-waste project. So we actually had quite a good basis to go on, and we're just enhancing the carbo-waste database and examining questions that remained at the end of carbo waste. So we wanted to determine the inventory and distribution of carbon-14 and factors that may control these within various graphites. What's the release rate and speciation of gases and dissolved carbon-14 that comes off graphite, and assess the impacts of selective waste treatment options. Again, the challenge here is diversity of national interests. The amount of graphite waste people have and whether or not it's planned for surface or deep disposal. So some of the highlights. We've got a detailed understanding of the distribution of carbon-14 within the waste. We have an improved mechanistic understanding of how the carbon-14 is released from graphite. So it indicates a small releasable fraction of carbon-14, with the majority of it, probably somewhere in excess of 95% of the carbon-14, actually being intrinsically bound and fairly much unreleasable. And of the carbon-14 that does come off, you end up with you observe an initial fast release followed by a long, slow-term release. And this gives you some indication of what you might want to take forward into a safety case, into a performance assessment model. It also gives you some robustness that, although your carbon-14 inventory in your graphite may be quite high, work we've undertaken so far indicates that most of it is intrinsically bound and is not readily releasable under repository conditions. And again, there's a final report available. So those were the sort of technical work packages within CAST. They provided a lot of data, and as is sort of fairly typical of the way projects are set up, we then considered the relevance of this new information to the safety case. We have a lot more data, we have a lot more understanding, we have a sort of greater depth in our understanding. And this leads to an improvement in the treatment of carbon-14 in safety analysis or safety assessments. So we've enhanced our knowledge of speciation of carbon-14 when it's released, the IRF, the release rate, and enhanced the robustness of our scientific understanding that we can record when considering carbon-14 in the safety case context. There are some challenges. There are a lot of people to get to work together, a lot of organizations to get to work together. This takes time. It's not insurmountable, but it takes time. You need to make sure that you do the groundwork that the various organizations are working in line and in a collaborative manner. You need to recognize that there is a diversity of national disposal programs, so we just need something to reflect on. And also, abstraction of data and uncertainties from experimental programs into safety case work is always something we need to think about anyway. So some of the highlights, we've got a better understanding of the relative importance of carbon-14 for different host rocks. We looked at all of clay and crystalline and salt in varying levels of detail. Understanding of the relative importance of carbon-14 for different waste types. So for spent fuel, for example, it's likely that carbon-14 will decay in a long-lived canister, unless, for example, you're looking at a canister failure scenario. And an understanding of the relative importance of carbon-14 depending on the repository location, so surface versus deep. I think probably most long-lasting of the legacy of the CAST project, we've produced a lot of useful information for safety cases, various national programs, as well as for underlying safety analysis. And again, there's a final report if you just wanted to read a one-stop shop of the upshot of work package 6. Key issue at the outset of CAST was to make sure that the results we got were known about and disseminated as actively as we could do, just to make sure that people knew the work we were undertaking, and also once the project was over, which it is now, that the work we undertook is still accessible, and accessible on the multiple year scale as well. So people coming back to this issue in 10 years' time, in 20 years' time, have the database to hand and can make sure that they pick up where we left off. So we held a number of dissemination workshops. for waste management organisations, regulators and waste generators. These were public. We've provided a continuous update of the development information in a series of reports. We've also undertaken presentations at scientific fora, scientific publications and newsletters, so scientific publications in peer-reviewed journals. We also undertook some training courses to actively train early career participants in cast activities. And there's the website, which is still active for Work Package 7. But if you just go to projectcast.eu, you'll find the website of the project itself. And from there, you'll be able to access all the reports I've been mentioning and all the underpinning reports. So a number of whole project meetings. I know this is common, but it's something not to be underplayed, the importance of getting together on an annual basis at least, to make sure that you can exchange knowledge, can change experience of your project, and make sure it runs smoothly. So we had a number of whole project meetings, and then we finished with a public symposium in Lyon in 2018, which is where this photo is from. Oops. As I mentioned about outreach, dissemination of results. That's the website where all the reports are based. We also produced a special edition of the Radiocarbon Journal. So this contains over 20 papers from this symposium, and that's both cast related and people who weren't participating in cast but came and spoke at the symposium anyway, so we made it an open publication. It's accessible on this phenomenally long website address, but if you just go to Radiocarbon Journal and look in the archive, you'll find this journal here and all the papers therein. But there are papers looking at steels, circuloids, spent ion exchange resins, graphite, and also safety assessments in the context of the cast project, Carbon-14. So some of the objectives, how do we do? We wanted to gain a new scientific understanding in relation to Carbon-14 in wastes and mechanisms for its release. We believe this has been clearly achieved. The work is of relevance to safety assessment. It's been documented now, it's in peer-reviewed form. It's suitable for deployment within safety analysis and in performance assessment and in safety cases as you choose to take it forward. And we also majored on dissemination to stakeholders. So we've produced over 100 reports on the website itself, plus over 20 papers. So we're trying to make sure that the legacy of cast is accessible. And we have provided an opportunity for early career researchers. So on my final slide, I'd just like to say thank you for the various folk that have been participating and have led various aspects of the project. I showed you the logos of all the teams earlier on, and these are just some of the people who had sort of leadership roles. So Christoph, obviously, from the EC. I'm not actually the original coordinator. I stepped up when the original coordinator retired. So I thank Steve for his contribution and his opportunity. And then we have various work package leaders. And also Fraser and Urker both provided sort of independent internal scrutiny to the project. So it was a way of making sure that they kept us on track. We were kept on track as the project progressed. Thank you very much.
Thank you very much, Simon. So I hope you will get the gift as well. So when Christoph is back, I think